Okay, I'm just going to see if I am live. Just 1 second. Yes, we are. Right, so I've been doing a little bit of work. On this particular video, and I'm sure you guys all know what we're going to go on about. Hello, Crow XE, nice to see you in. Now, I did a little live stream this morning, and I was messing around with this video, and I was trying to figure out where it actually hit. And I think my original calculations had taken it to essentially about here, just beneath the perceived horizon. So I decided anyway, I went out for a bit of a walk, cleared my head, came back and thought, you know what, I'm going to revisit it. And this time I'm going to do it properly. So I'm going to literally go through this bit by bit, and we're going to get a clear and concise point as to where this actually hits. So this is the presentation. Nice to see you, JJ. Right, first and foremost, let's get some things straight. So wherever there's an inferior mirage, we always get this stretching going on. There's always a stretch going on. Doesn't matter where you go, it always stretches near the horizon or the perceived horizon. Now, this is quite evident in this particular image of this lighthouse. Let me just get the shape up. So if I put a line through from there to there, which is where the chimneys are, for instance, you'll see that it retains its aspect ratio on the width. But when we scroll that to the top of the chimneys there, and then we put another one to the top of the chimneys here, let's just do that correctly. And then we do it from the top of the lighthouse down. Now what you'll see is when I now measure this same part here and place it from the top of the chimney down, can you see how stretched it is in compared to the top of the chimney pots? So we always know that we get this stretching effect going on right around here. So in order to avoid that, what we have to do is exclude the frames that are closest, well, the frame closest to the inferior mirage. Now, let's go back to the image. So what I've done here is I've gone through this frame by frame, and as you can see, I've now put the next 4 images in, 1, 2, 3, 4. And what I've done is I've scaled the first one to line up with the number 10. The bottom of this is at number 10. So that what I'll do is I'll count 1, 2, 3, 4, and I'll know how far this has traveled over 4 frames, and then I'll be able to run it back and get a calculation. So in order to do that, next frame, here we go. So I've put these lines in. Now, as you can see, first one is scaled directly on the number 10. And then we've got 1, 2, 3, 4. Hi, Del. Nice to see you in. Nice to see you in CGI Rantian National Memorial Gardens, is it? Yep. So these 4 frames consist of 4.3 millimeters on this ruler. So all of these are fitting inside 4.3 millimeters. Or is it 5.3? 5.3, my mistake, 5.3. So 1, 2, 3, 4, 5, 5.3 millimeters. In the next frame, so this is where we're going to get a little bit of stretching going on towards the bottom. This very last image here is going to be slightly stretched, even though we do have a definitive center point. It is still going to be stretched on the top image. So we're going to take obviously references from here, but this is the last 3 frames. 1, 2, 3, 1. Then we get an inferior mirage. Then we get another inferior mirage, and you can clearly see on the next frame where we're going to end up with this inferior mirage line. So let's zoom in, and we've put the inferior mirage line in right through the center, and it ends up at essentially 1.2 millimeters above the perceived horizon. Right, so now that we've got trajectory of the object falling down, let's get the next stuff in. Now, what's interesting on this, now I'm sure if Reds or Slice Barcane does this, they'll also see the same effect happening here. But the inferior mirage actually happens slightly lower down. So it's actually saying that the inferior mirage of the splash is actually slightly nearer than the trajectory of this object that was falling. So that tells me that in some way this object as it was falling was actually coming slightly nearer towards us. It's actually working its way towards us, and the splash was being pushed slightly this way, which you'll see on the next frame. You'll see that on the inferior mirage. Now, I noticed this morning when I did it, and I got the same effect when I repeated the same on this. And that's that the inferior mirage is slightly lower down. And that tells me that the inferior, whatever this splash is slightly nearer than where the object was coming down this way. And that's been demonstrated loads of times by me over the past. If the inferior mirage is lower down, it's slightly nearer. Hi, Brian. Nice to see you in. So anyway, so now we've got some details here. We've got 4 frames going along here above this point, and we've got all these 4 frames going down here. What I've done is I've eliminated frame 1, which is this one, where we're going to get that stretching going to happen, as showed and demonstrated here, what happens with this stretching. And what we're going to do is we're going to measure the distance between these 4 frames here on the splash, right? So we've got from 2.1 to just over 5.05. So that's the difference. That's how much the splash has taken up over 4 frames, right? So let's put them on so that you can see that. So 5.3 millimeters is the distance that these 4 frames have traveled on the object falling, and the splash has returned 2.95 over these 4 frames, right? So that's the splash going back up, much slower, much faster going down, much slower going back up. So I'm trying to figure this out. I'm trying to think, well, what would, well, obviously I'll give you the results in a minute, but what would be the ideal circumstance to get a result where we would get this? And the only way I can figure it is this. So we've got 5.3 divided by 4 equals 1.325. So that means that it is traveling 13.25 millimeters every frame down. And then the splash going up is 2.95 divided by 4 equals 0.737. So that's 7.37 millimeters going up, right? So it's almost half as slow, but not quite. And let's go to the next frame. So the next frame is really interesting, actually. So what I've done is I've taken out the last clear image that we had of this, tumbling capsule. So as it's been tumbling along, I've taken this screenshot of this and I've placed it along here because we know that there's the top of the capsule, there's the top of the capsule. So we can get a rough idea of pretty much where this is actually going to be in relation behind the inferior mirage. Now what that does is it places it about 4.2 millimeters or so above the actual horizon, something like that. So it's very close, very, very close. In actual fact, if you're going to divide it into per frame, with it being 1.325 or 13.25 millimeters as opposed to 4.2, it's literally about 1/3 of a frame. So 1/3 of a frame, and it would be at this point here. So very close, very close. In fact, almost instantaneous before it would have got to that point. So let's go back. So with this being so close to the horizon, we've got 3 frames. Now, if this hit was 0.33 of 1 frame, so 1/3 of a frame, so almost instantaneously, what would make this bounce up, this inferior mirage bounce up, and the top of these waves get to a height of just over 20, so about 21 millimeters? Well, if we know that these are moving at 0.737 per frame, then 3 frames of this would be a little over well, just about 22 millimeters. So I'm going to say that this object, almost instantaneously, just after the last frame was taken, struck the ocean right here. And then by virtue of the fact that it took 3 frames to go back up, the water splashing up at 0.737 or 7.37 millimeters per frame would have taken it 3 frames to climb up 1, 2, 3 and get to this position here, which is relative to the first position noted on Red's video. Now, that's the only way, using all the calculations that I can figure out, that I can get this result. Now, I've been doing this all morning, most of the afternoon as well, and I've been trying to figure this out. The only way, like I say, this is so close to the horizon. This is so close, it's almost instantaneous. Now, by virtue of it almost touching the water, and then it taking 0.7 millimeters per frame to actually creep back up and get into this position, it has to be, this is the only way that it could have struck actually at the perceived horizon. It struck at the perceived horizon. The whole of this object disappeared behind the inferior mirage, and then this bounced back up. And it took 22 millimeters to take it back up to this position here. And this being the first frame, as I said, you can see it slightly stretched. You can see it slightly stretched. You can see it stretched in relation to this because it doesn't match up 100%. And by virtue of something just like this, explaining how this mirage, just when it gets nearer the mirage, it stretches. You can see the stretching going on between here and here. We know that stretching is happening here, which is just pushing it ever so slightly. And that's the only way that I can actually make this work. I've tried every other calculation possible, but with the speed that this is traveling, the distance that it's covering, the object in relation to the water when it actually went from view behind the inferior mirage, where it went from view right here, it was almost at the perceived horizon. And by the fact that this splash reached 21 millimeters going back up, and it's traveling at 7.3 millimeters per frame, then it has to have struck right here. There's no other way that it couldn't. There's no other way that it would have worked. Whatever calculations that Reds is going to come up with, or /Arcane, or anything like this, the maths don't lie. The maths don't lie. You can't get this calculation to work any other way. I'm sorry, it just doesn't work. And the only way that they're going to perhaps try and wangle something different is if they try and claim that this tiny bit of stretching that's going on here, and they might be able to wangle a millimeter or a couple of millimeters here or there. But even if they were able to do that, it's still going to place it right behind this. Even if they twist it, it's going to place it right down just here. But just on pure knowledge of how inferior mirages work, knowing the calculations that have been put into this, and I've spent all day doing this now, it can only have climbed up to this position on the chart at 21 millimeters as its speed. That's its speed that it was traveling. You can see that over here. So 1 frame, 2 frame, 3 frame, 4 frame, and it's traveled 2.95 divided by 4 equals 0.737. So for 3 frames of that would be 21, and obviously that's 21 right here. So there we go. There we go. Ranty, why does it disappear? It goes behind the inferior mirage, Brenda. It goes behind the inferior mirage. You know it goes behind the inferior mirage because I actually showed it you this morning on the video that I uploaded this morning. Thank you, Earth is seriously flat. Thank you very much. Do appreciate the super chats. Let's see. Right, Ranty, how many frames between the last frame of the capsule and the first frame of the splash? 3. 3 frames, Bob the Science Guy. So this was the last frame here, this one, and then it was 3 frames of nothing 3 frames of nothing, and then this. How can you go behind a Mirage for 3 seconds? Let's see. Let's get something over here. Let's see if I can wangle this over. Just 1 second, guys. New window. Let's see if I can drag that across. Yep, can do. There we go. Happy days. So, YouTube. So let's bring up myself, Ranty Flat Earth. Let's find our videos. Let's find the sneak boat, wherever that is. Just bear with me, guys. The only reason I'm going through this again is because there's probably a few people that haven't actually seen this, or Brenda has actually seen this stuff before. She's just trying to take up my time. And that's okay. Sneak boat. Here we go. So how can it go behind the inferior Mirage? Well, there we go. Here's a boat behind the inferior Mirage, Brenda. This is a boat that's about 90 feet tall. Half of the boat is hidden behind an inferior Mirage. Now, my elevation is 30 feet, and the distance is 7 miles to this boat. There should be no hidden at all. And if you just use geometric, I think there's 2/3 of 1 inch, 2/3 of an inch if you just use geometric. But clearly there's about 45 feet of Mirage going on here, hiding the bottom of this boat. So that's where Red's Rhetoric's capsule is. It's behind this inferior Mirage, behind this blockage. The inferior Mirage is an atmospheric blockage, which the Rumpus is quite happy to agree with, and a few other people, bearing in mind. Even you, Brenda, I'm sure will know that the inferior Mirage isn't where the curve of the Earth is anymore. You know, that's long debunked. So as I say, so there's the inferior Mirage. The object falls down, it falls down, it falls down. It's behind the inferior Mirage. It's still falling. It hits. It goes back up. The splash is going back up, but the first parts of the splash are behind the inferior Mirage, and then poof, it's there. Dead easy. Dead easy. But where is the rest of the boat? Brenda, it's behind the inferior Mirage. What have I had to say? It's behind the inferior Mirage. You know it's that. You should have direct line of sight to this, Brenda, but we don't. The hull is behind the inferior Mirage. It's not behind Earth curve. I'm high enough to look over Earth curve if there was Earth curve there, but there isn't. So it wouldn't matter if it was flat, globe, concave, hollow Earth. It wouldn't really make any difference whatsoever. I should just have direct line of sight to this boat. But I don't. I have a blockage, and the blockage is the inferior Mirage. And I've demonstrated this, not just this time, but hundreds of times over the past couple of years. Brenda, you know this. You've seen this demonstration, not on this particular image, but on dozens of other images too, and videos that clearly demonstrate that the inferior Mirage hides things at the bottom. So I don't know whether I should really go through too much. I could do. I could go through the game is over. Where's that one? I'll be one of the recent one. Game over. Here we go. Brenda, just for you. Just for you. Now let me find the truck. The truck's the best one. Just let me find it. Oh. Here we go. Right, okay, so here's the truck one. Same elevation, same position off the railings, same tide height. Everything's the same, except on one day, we just have clear line of sight to the other side of Barrow and Furnace, including a house right in the corner over here. Extra land down here, a truck on the shoreline down here, Brenda. Just a very nice day, very clear, and we've just got a clear line of sight to this, just an absolute clear line of sight, no problems. When there's an inferior Mirage, however, obviously you can see the mast here. And if we place this truck down here, where it would be, let's suppose if it was here on this particular day, it would be behind the inferior mirage, the same as this land over here, the same as the house that should be visible, that would be hidden behind the inferior mirage. Everything's hidden behind this inferior mirage. Now, Brenda, if we replace the bottom of this truck and say this is a boat, and there's the top of the boat here with the mast, and here's the bottom of the boat, here's the hull, right? So we can't see the hull, Brenda, because the hull is behind the inferior mirage, but we can see the top of the mast because it's visible. It's out of the inferior mirage, but anything behind the inferior mirage, including like this truck, is blocked out of view. You can't see it. So whenever we see an inferior mirage, we get blockage, not earth curve, it is blockage. And both of these videos were done with the same camera, same position off the railings, same tide height. Here's the two videos side by side, so you can see that demonstrated. Same place off the railings. I do a 360 to show you exactly where I am. There's the tide being out. There's the tide being out. Same place off the railings. I even do a panoramic and I zoom in to show you exactly where I am. So there we go. And you zoom in. All these have different numbers. So it's for the lifeguards to come and check. So if you fell into the water and you was in trouble, you'd reference BLO 97 so that the lifeguards would know exactly where to come and find you. The next one down is BLO 96, 95, etc. this way. And of course, obviously, if I go back to the first video, let's see if I can get that in focus. Yeah, there we go, BLO 97. So same place off the railings, same position, everything same height, two videos filmed, one with an inferior mirage, one without. Same place off the rails, same tide height, everything. And we had blockage, Brenda, just blockage. So there we go. Right, so now that I've demonstrated that, and we go back to this, yeah, the only way, like I said, the only way that this works, the only way that this mathematics works, when we've got this traveling up at 7.3 millimeters per frame, which is this point here between these four, 1, 2, 3, 4. The only reason that works and gets to this position on the first frame is if this almost instantaneously hits the water. And as we can demonstrate here, the frame, when we last see it all in its entirety, and then we take that out and we superimpose it here, you can see that it's almost, it's just 4 millimeters off, which is just 1/3 of one frame off the actual perceived horizon. So it's most likely that this almost instantaneously hit, and then it took 3 frames because the splash was traveling at 7 millimeters per frame, and it took that long for it to get up to this position here where we actually see it. So there we go. There we go. Right, so I'm sorry if I'm missing anybody in chat, by the way. Just bear with me. Right, let's see what's going on. Let's see what's doing here. So, right, so Bob the Science Guy. Hi, Roxanne Bass. Nice to see you in. Right, so 3 frames represents about 4 centimeters by my calculation. Assuming that half of the frame means no, Bob, no, you're quite a way off there, my friend. What we've got 4 frames here, so that's 1 frame. That's 1 frame here, 2 frames, 3 frames, and that's 4 frames. So from the bottom of this capsule visaged here to the bottom of the capsule here, after 4 frames, it's traveled 5.3 centimeters or 53 millimeters. So you're way out there. You're way out there. So each frame it's traveling 13.25 millimeters, or close enough to 4 centimeters, but still not quite. So then you went on to say that assuming half of that is the time to fall means that it went 2 centimeters below the last frame of the capsule. No, absolutely not. Absolutely not. Not at all. Absolutely no way. This was traveling at 1.3 frames per second, right? Its last known position was here, which was just 4 millimeters off the perceived horizon, right? Now, if that struck almost instantaneously, which it would have done, it would have taken 1/3 of a frame to reach the perceived horizon, right? Then we have a much slower return rate of the water. The capture wall's trapping down here at 13 millimeters per frame, and the water's going much slower at 7 millimeters per frame up. So it took 3 frames for it to get 21 millimeters. And if you look on the first image of the return of the water, and as you can see, it is actually just over 21 millimeters. So it's absolutely clear that this object struck right down here almost instantaneously, and then it took 7 and 7 and 7, 21 to go back up again. And how you can derive the pace that it was going of the water, you can go from frame 2, 3, 4, and 5 of the water as it pushed up, right? And you can calculate by these 4 frames how fast the water was traveling, and that gives you a value of 2.95. 2.95 divided by 4 equals 0.737. So, it's quite clear what's going on. Right, okay, so no, check your math again. 3 frames would be 1.7. No. You're assuming that it took an entire, Bob, honestly, you're assuming that it took an entire 1.3 centimeters, or whatever, 13 millimeters to go all the way down again. No. That's what I've worked the calculations out, Bob, and that doesn't work. 1.3 down and then traveling 0.73 back up again would mean we wouldn't see the splash. We wouldn't see this splash until around about frame 5. There would be 5 missing frames. So that can't possibly work. The only way that you're going to get this mathematics to work, Bob, is if, as we know its last known position here, it almost instantaneously struck the water, right? Because it's only 1/3 of a frame away from the perceived horizon. So if it struck almost instantaneously, then the return speed of the splash at 7 millimeters per frame would have taken it to exactly this position, 21 millimeters, as envisaged here. The only way, juggling all the mathematics, and I've done this 4 or 5 different times today, been through trying to find out what is the actual point that it struck and how long would it take. And this is the only mathematics that works if it actually struck right here, almost instantaneously. Hi, Arwin. Nice to see you in. Nice to see you in Flatzoid. Ranty, can you go check a video? Roughhouse did the splashing. And hits the apparent horizon, vanishes into the Mirage and hits the apparent horizon. So are you trying to say, Flatzoid, that he agrees with me, with my calculations? If that's fine, that's fine. Are you using the original footage from Reds? Yes, I am. Yeah, I am. And like I said, I mean, it's quite easy to see how fast this object was falling, because the fall rate is very evident. You've got nice clear imagery of the fall rate, so you can quite clearly see that that's 1.325 centimeters on this ruler per frame. So yeah, it's all very good. Phil Blacker, the desperation is 100% real. What, from globe Earth or flat Earth? I'm not look, all I'm trying to do is research where we live, and I do get a little fixated on some things sometimes, and this just fixated me for the day, and here I am with the results. The only way that you're going to get a return value of this splash on the first frame of the first splash that measures 21 millimeters high. The only way that you're going to get that value after working out the speeds that the water was traveling up at 0.737 was that if this almost instantaneously hit, and to be fair, that would fit in absolutely perfectly, because essentially this water is traveling up at 22 millimeters and it's hitting at 21. So that 0.1 of a millimeter is probably the time that it took for this to actually, that 1/3 of a frame to hit the water. So it's likely that it hit probably just even, maybe just even above the perceived horizon, behind the inferior mirage, and splashed up. There's absolutely no way the calculations, you can't fudge the calculations any different to get this, to get a result when you've got it all written down like this. You know, this is just pure mathematics. Yeah, Bob, yeah, it is 3 frames that's missing. There's 3 frames that's missing, right? So we've got frame 1, 2, 3, 4, 5, 6, 7, 8. So let's say that's 8 frames, and then we've got, this is obviously just an image that I've overlaid from here just to get that calculations, but this is the last one that we see, so that's 8. In fact, I might have it on. Let me go back and just show you, because I think I've actually got it. No, I'll keep it with the lines in. So there we go. Anyway, so we've got 1, 2, 3, 4, 5, 6, 7, 8 frames, and then we go 9, 10, and 11 are not visible. 9, 10, and 11, and then you go on to 12, 13, 14, 15, 16. Right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 missing. 12, 13, 14, 15, 16. So we've got 3 missing frames. And we've got a bit of stretching going on both the inferior mirage of the last capsule here and the inferior mirage of the splash here, which is quite in keeping with what happens with inferior mirage stretching. As you can see, I've put these lines across to the top of the chimney, and you can see that the height of the lighthouse when it's in inferior mirage is stretched, and when it's normal and it's not being stretched, it's much it's not quite as stretched. So when we get an inferior mirage, we do get this stretching that happens right near the water line. So excluding this first frame, because we know that there's stretching going on there, and that's why I've calculated things that are visible. So these 4 frames here that are quite visible after the stretching, and these here, it's pretty easy to figure all this out. And like I say, the only way you're going to get mathematically to a position where this is returning up at the speeds involved is if this hits almost instantaneously, and then the return speed of the water at this particular speed would reach this point here on the top of the first frame. Hi, Super Dave. Right. Hello, everybody. Skyfly Bry. Hello. Nice to see you in. Right. I'll just go with the original film with the 11 frames uncut and redo it just to confirm. Yeah, that's fine. That's fine. You know, I mean, I'm quite sure that you know, I've scaled everything correctly. Red's Rhetoric's, you know, his camera was ever so slightly out, so I had to just readjust it just tilt it ever so slightly. I think it was 0.4 of 1 degree, just to level it out to make it flat. And then once I'd done that, yeah, I could put all these other stuff in and everything works out fine. Phil Blacker, so much desperation from frauds who are making money off gullible, stupid people. So I didn't get to see whether you was responding to me before there. You know, I'd like to see you guys have a go at this. You know, I mean, if you think that you can have a go yourself and see whether or not you can find anything different. You know, we've got speeds here. We've got definitive speeds. We've got things that can be calculated in Red's video. I don't see a problem. I genuinely don't see a problem. And to be fair, I'm not even saying that it's proof of Earth curve or flatness. That's the thing, because we don't know where this object fell. This object may have fell just 10 miles away, for all we know. And Red's rhetoric could have been at an elevation of 45, 50 feet. Again, we don't know. We don't have all the details. We don't know whether it's proof of Earth curve. We don't know whether it's proof of flatness. What thing we do know is that it certainly isn't going behind the perceived horizon. That's the one thing that I would point out. Now, does it mean that Reds is right or Reds is wrong? No, it just means that the object that fell and struck the water didn't strike the water below the ruler. It means that it could only have hit the water at least at the perceived horizon or slightly above, due to the mathematics of the return speed of the water and the missing frames. That's the only way that it could have happened, having reviewed all the calculations that were possible. And that's it, basically. You know, like I said, I mean, it's quite possible when Reds goes back, he might say, well, my elevation was 45 feet. We've got the data. I've worked out all the angular sizes. I know my zoom length. And essentially, we can triangulate this object to strike in the water at 10 miles away, in which case it's neither proof for flat Earth, neither proof for globe Earth. But to simply assert that it's behind Earth curve, you know, when it's demonstrably not behind Earth curve, you can prove that. You can work that out. Anyway, so I wanted to keep it quite concise and quick, and yeah, I think I've managed to do that. I think it's been a profitable day, worthwhile, definitely worthwhile for myself to spend the day doing this. I feel, you know, that it's something that other people should put a little more time into too, and they can figure this stuff out for themselves if they actually work on it too. Sorry, David Grevery, correct me if I'm wrong, but are you suggesting the speed of the water splashed upwards is the same as the speed that the vehicle was descending? Absolutely not. In fact, if anything, I don't know where you got that from, but you can actually see the speeds of the return per frame. So this is per frame. So the object is falling at 1.325 centimeters or 13.25 millimeters per frame. And the return splash is traveling upwards at 0.737 centimeters or 7.37 millimeters per frame. So much slower. The splash is going much slower. And the only way that you're going to get a value where this first frame of the splash, the top of it, hits the number 21 on the ruler is if this object almost instantaneously on its last known position, almost instantaneously strikes the water, because the travel speed of the splash would take 3 frames to get to that position. That's it. Right. Okie dokie. So thanks everybody for stopping by. And hopefully we'll get a guest on for tomorrow for the roundtable. So hang on, what's this, Bob? Nice job, but you still haven't accounted for the missing 3 frames. Yes, I have, Bob. Bob, are you not listening, my friend? There, like literally, right? Literally, it's here in front. You know, I mean, you're a clever fella. I had you on my channel this week, so I know that you're kind of clever. Well, you should be, and you should know that. You know, I'm explaining where those missing 3 frames are. They're behind the inferior Mirage. If you don't know what behind the inferior Mirage is, you're quite welcome to look back at the video this video, because I actually show you what things behind an inferior Mirage look like. Yes, I did. Yes, I did. So the invisible object behind this line here. So we've got behind this line here on the drop and the return, which is slightly lower, proving that the splash is probably slightly nearer. All this is atmospheric blockage, the inferior Mirage, and the object goes behind that, behind the inferior Mirage, the same as in, where are we? Same as in this video here. So let's go back to the truck. Let's find the truck. I'm sure you guys just keep me on here to try and make the video length so long that people don't really want to watch it any longer. I think that's what it is, because I like to do the nice and concise video, and people hate people repeating themselves. And I feel like I'm having to repeat myself because you guys have already seen this presented to you, and you just deny it. All right, here we go. Right, let's go back a tad. Play. There we go. Here's an inferior Mirage, guys. Same place off the railings, same tide height, same elevation, everything. No difference. The only difference is the inferior Mirage on the bottom and the non-inferior Mirage at the top. Well, whoopee-doo. There's no inferior Mirage at the top, and you can see houses in the background, land, a truck on the sands down here. But when there's an inferior Mirage, all of that is missing. It's all hidden behind an inferior Mirage. Atmospheric blockage, not Earth curve. It can't be Earth curve on one day and not Earth curve on another day, because there's no difference in the tide height, there's no difference in the elevation or the exact spot that I was filming from. The only difference is an inferior Mirage on one day and a clear day on another. When there's an inferior Mirage, things get blocked out, things get hidden. Now, if this truck was Red's falling sky thing, capsule, falling down, and it's gone behind the inferior Mirage, well, what do you know? You can't see it because it's behind the inferior Mirage. Missing frames? Well, there's your missing frame. On one, you see the truck. Now you don't. You see the truck. Now you don't. It's behind the inferior Mirage. One frame missing. Two frame missing with the splash going back. Three frame missing with the splash still going back up. It's all hidden behind the inferior Mirage. You don't see it because it is blocking your line of sight to things. Just in Red's image, let's bring up Red's image again. Just in Red's image, behind this inferior Mirage, where the truck would be, the object is falling, it's falling, it's falling, it disappears behind the inferior Mirage. The same as the houses, the same as the land in the distance, it's all behind the inferior Mirage. The return splash that's going up, is all behind the inferior Mirage until you can see it. And you end up seeing things when you can see it. It's as simple as that. You end up seeing things when you can see it behind the inferior Mirage. There we go. Dead simple. It really is simple, guys. I've been working on this for the past couple of years. You know, this isn't the only stuff that I've got. I can show you reams of data, including this. Reams of data. Behind the inferior Mirage, Bob. Right. Will you point out where the horizon is on an inferior Mirage, Ranty? No, I won't point out where the horizon is, because when you've got an inferior Mirage, you can't tell. You have a slight bit of stretching, you have a bit of warping going on, everything's unclear. As you can see, that it's just things get messed up. Even out of the inferior Mirage, this spire is still slightly out of focus and warped and twisted. And if we go over to the lighthouse, for instance, over on the right, you can see just how dramatic that effect is. You can see how wiggly this object is. This lighthouse is here. You can see how thin it makes it, how stretched it makes it, how wiggly it makes it. Not clear at all, but on a clear day, you just see it very nicely, very crisp. So asking me to say where the horizon is when there's an inferior Mirage, I can't do that, Bob. Don't think anybody in the right mind could do it. What we can say, though, is that, see this land on the bottom here? See this land that we should see? See this sand dune that's here? This is a sand dune, Bob, that's blocking the house behind this lighthouse. This is a sand dune here, right? Well, the sand dune isn't visible in this image, right? It's not visible in the image because it's behind what's called an inferior Mirage, right? Behind an inferior Mirage, Bob. Same height, same tide height, no difference, just an inferior Mirage on one day, which causes blockage, and no inferior Mirage on this day where you just see everything, right? So when in Red's video, where we have an inferior Mirage, that's where the object is. The object is behind the atmospheric blockage, Bob. This is the point where I educate you on optics. This is the point where you're stepping into my domain and you're talking about things that I know things about, right? You might know things about medical stuff and you might think that you're clever about other things, but when it comes to optics, Bob, this is where I educate you. So behind the inferior mirage, that's where Red's capsule fell. It struck almost instantaneously at the water, and it took 3 frames traveling at 7 millimeters per frame for it to reach this point here, where it finally became visible in the first frame here. And that is it. That is it. That's the only way that these mathematics work. I mean, you could perhaps argue a millimeter here or a millimeter there, or a tiny bit here, a tiny bit of a wiggle there, but you're not going to make it any different. You're not going to put the object striking the water down here behind Earth curve. It's never going to go that far. You're never going to put it here either. The only way that these mathematics work is if this struck almost instantaneously and it took 3 frames for this water to splash back up. That's the only way you're going to do it. The only way you're going to do it. The horizon is between the lighthouse and the reflection. Are you sure, Bob? Right, okay. Somebody actually said you're going to embarrass yourself here. And Bob, you know, I have to agree, they're quite right. You are going to embarrass yourself right now. You see, these 2 videos were taken from exactly the same spot with exactly the same tide height, exactly the same position, similar kind of days, no real difference. Here's 2 screenshots of the same location. You can see that the tide is out here on this one. You can see the tide is out here on this one. You can see that I'm actually at the same position on the railings. You can see it because in both images I turn around and I do a 360 and I point the camera at the actual RNLI BLO 97. So if you get stuck in the water and you're drowning, people can reference this BLO 97 so that the lifeguard can find you. And it's off the railings, exactly off the railings. And if I go back to the first video, because I do first one video compared to the next, and then we retract the camera again off the railings, I turn around and I zoom into BLO 97. So Bob, unless you're saying, right, that in this particular image, where are we? We had looming on one day and we had Earth curve on another. If that's what you're trying to say, then you're absolutely insane. I can also demonstrate it another way. Let me... God, who's messaged me now? All right. Yeah, I can also demonstrate it another way. I can go up here and I can go to, where are we? Sneak boat. There we go. I love this. Sneak boat. Here we go, Bob. 30 foot off the railings, right? Now then, the distance to the boat is 7 miles away. There's no Earth curve between myself and that. I should have direct line of sight to this boat, Bob. There should be no problems with me seeing all of this boat. Now, this boat is 90 foot tall, Bob, which means that 45 feet of this boat is hidden, Bob. 45 feet is hidden behind an inferior mirage. Now, I should have clear line of sight to this, Bob, because it's 30 feet elevation and it's only 7 miles away. But guess what? I don't have clear line of sight to it because the Earth curve shouldn't even play a part, nor should flat Earth, nor should hollow Earth, nothing like that. I should be able to just see it. And the only reason I can't see it is nothing to do with Earth curve, Bob. It's to do with the atmosphere, the inferior mirage blocking it, because I'm high enough to avoid any Earth curve, Bob. It's a simple fact of the matter. There should be no problem with me seeing this boat, Bob. Bob. But that's an inferior Mirage of a boat 7 miles away, 90-foot high boat. Should have no problems just seeing it, but it's hidden behind an inferior Mirage, Bob. Not Earth curve, Bob. Right, okie dokie. So, the last 4 frames of the splash. Right, I'm 20 minutes behind. Do you think that the last 4 frames of the splash reprise the last 4 frames of the splash were the second, third, fourth, and fifth frames of the actual splash that was seen, right? That's what we actually captured there. Now, if you break it down into time, we're looking at 30 frames per second. So let's bring up the image. So we're looking at 30 frames per second. We had 3 frames of missing. My calculations would say that would be frame. If that hit instantaneously, we're looking at 3 frames hidden, 1 frame unaccounted for due to the stretching. So frame 5 would put it at 1.5, something like that. About 1.10. So just over a tenth of 1 second. So just over 1/10 of 1 second after impact would have been where this water was visualized. So essentially, yeah, I'm going to say it's pretty consistent. You know, the height relations between these are pretty consistent. There doesn't seem to be an awful lot of difference between frame 2 that's visible, 3, 4, and 5. They seem to be growing at a relatively the same amount. So it's showing that it is still exploding upwards with quite a lot of velocity. Obviously, the very, very first frame and impact is probably going to have the fastest speed. But in relation to this particular calculation, I don't see a problem with it, because these are the 4 that we can actually see. This one here is with a little bit of stretch on it, just down here in the inferior Mirage, which stretches it down, which is why it looks just in the wrong position for the midpoint. But these are all okay. These are all okay. 2, 3, 4, and 5, they're a consistent step upwards. It seems logical to use them as a speed, which is just less than, well, just over 1/10 of a second after impact. Yeah, it's pretty close enough. Pretty close enough. It's not enough to make a huge difference anyway. Anyway, right, guys, I wanted to keep this quite concise, and I've been going on for nearly an hour now. A massive thank you again to Earth is Seriously Flat, who did another super chat. Flat Earthers know center of Earth is paradise at the North Pole, and globe zombies believe center of the Earth is molten magnetic lava, aka a hell. Be smarter. Thank you very much. Right, so that's pretty much all I've got to say on this. 3 missing frames, a speed of 7 millimeters per frame for the splash, superimposing the last known image of the capsule in its entirety next to the inferior Mirage. The top of it here places it at its bottom here, almost instantaneously hits the water. The return splash takes 22 millimeters to actually go up. And what do you know, the first known position of the first inferior Mirage is just on 21 millimeters, so it's within a margin of error. So yeah, I'm gonna say pretty much that's sorted. That's where it must have hit. It must have hit there, and the slowest return speed of the water placed it here. And the only reason, and let me just be quite clear, because I know that people are going to say, well, I know that Slice Barcane is going to mention this very first image and say, well, look at this here. Obviously, the inferior Mirage is starting at 1.1 centimeter, and it should be at 14 centimeter if Ranty is right. It should be at 14, but it's at 1.1. Well, no, because as I said, we get stretching going on. very close to the inferior mirage, and that's demonstrated. Let me just show you again here. These two black lines are lined up with the tops of the chimney pot. On the inferior mirage, and I've scaled this now, you can see that the inferior mirage is, there's the full length of the lighthouse as envisaged in here. And then when I put it on an image of the known lighthouse without an inferior mirage, it's much smaller, much chunkier, much shorter. So we know that these inferior mirages right at the horizon always stretch the object. So this first one, we can discount this stretching that's going on right at the inferior mirage. We can discount that. That's why I moved on to frame 2, 3, and 4. So, right, that'll do for now, guys. Thank you very much, everyone, for stopping by again, and I'll see you all in the next one.